it's an introduction to embedded Rust. You know, Rust runs on pretty much anything that has something called more or less a microprocessor. And I wanted to experiment with running Rust on microcontrollers. So microcontrollers are things like, I'm going to show you this little, oh, it doesn't want to, oh, first technical problem. The camera picture doesn't want to move on the other side. Give me 1 second. There you go. So this little thing here that we see is a microcontroller, right? So it has 8 kilobytes of flash memory and 512 bytes of RAM, right? So it's very tiny, and we are going to run Rust on that thing. And then there is another demonstration, which is this one, which is about 1,000 times more bigger and more powerful. Yeah. So this is to show you the extent of what we call microcontrollers. So let's go back to the presentation. So my name is Sylvain Vallès. I work in the clients team at Elastic. I'm responsible for the Java and Rust clients. And I've been playing with microcontrollers since 2010, that is more than 10 years now, starting with the well-known Arduinos and then like trying, putting my hands dirty on whatever came onto my desk. So this is more or less a private joke. I live in Toulouse, south of France, and well, I'm on the countryside, and we have lots of boars ruining the garden on a regular basis. So this is kind of like the running joke in my area. So why Rust? So I think I will skip that one because I guess you know what are the benefits of Rust. That is performance, compiled to native code, reliability because of its rich type system, and the productivity, which sometimes may seem strange to people who are just getting started, because getting started with Rust is hard. There is a steep learning curve. But once you get over it, well, my personal opinion, and also a number of people's opinion, is that you're very productive because it shifts the time. I mean, you spend maybe more time writing code and having code that compiles, but you save a lot more time on solving issues in production, because once it compiles, it runs. So embedded software, the specifics of embedded software is that it's bare metal. You run directly on the CPU. There is no operating system, or at least no real operating system. There are what's called real-time operating systems that are more or less like task schedulers and provide synchronization primitives, but don't go much further than that. Another thing that is specific to microcontrollers is, yes, you have a lot of peripherals with direct access. So GPIO, that is general purpose input output, that it's set high, set low to control LED, LEDs, motors, whatever. UART, which are known as serial interfaces, and then a few protocols on top of serial interfaces, which are used by almost every non-trivial peripheral that you can find. That is, as soon as you have like a, I don't know, a smart sensor or a display or whatever, they talk either I2C or SPI, which is a protocol on top of the serial line. Another interesting thing in Rust is that it can very easily do cross compilation. So I told you the size of my small microcontroller. There is no way I could run the Rust compiler on that thing. So I have to build the executable with a cross compilation. So today we are going to play with two little things that I briefly showed you. So the first one is the ATtiny85, which is really tiny. 8 bits, 8 megahertz. It can even run down to 1 megahertz. It has an AVR instruction set, which is more or less like very simplified RISC instruction set. 8 kilobytes of flash memory and half a kilobyte of RAM. Yeah, and we can do a lot of things with that. 6 GPIOs. So if you look at the chip, it has 8 pins. One is for ground, one is for 5 volts, and the other 6 are input outputs. It costs, if you buy it a single unit, 50 euro cents, which is more or less $1.50 cents as well. So it's super cheap, and if you buy it in large quantities, it goes down to a few cents. So it's used a lot, even if it's a bit outdated, because I think it started like 15 years ago maybe, but it's still used a lot because it's very robust, very cheap, and if you don't have complex needs, it fits perfectly. And the other one is a more recent one. It was released, I think, like less than 5 months ago. So it's the other. Sorry, the other end of the spectrum. So it's called the ESP32. It's a 32 bits microcontroller, runs on 160 megahertz. Other in the same family go up to 240 megahertz. The instruction set is RISC-V. So you may have heard of that one. So historically, the high-end microcontrollers have been using the ARM instruction set, but recently this new architecture emerged, and the interesting bit is that it's open source. So that means that vendors do not have to pay a license to use it, and we see a large number of RISC-V microcontrollers popping up. It has 16 megabytes of flash, so it's 2,000 times bigger than the tiny one, and 400 kilobytes of RAM. So yeah, and the price is a tiny €2. So it's really cheap. €2 is only this little metal box here with the Wi-Fi antenna. This is the module. What's around it is the development kit that exposes, you know, all the GPIOs as like nice pins, and has the USB connector with power regulation and so on. So let's start with the first demonstration. So the classic demo we do with the programming language is Hello World. So on our ATtiny, we don't have a display, so we are going to blink an LED. This is the Hello World of embedded systems. So I'm going to switch to IntelliJ. Yeah, so this is the one. So here's the code. Is that, yeah, this one. So if you ever wrote some code for an Arduino that may sound familiar, there are a few differences. We start here by taking peripherals, and we put it in a variable, which is device peripherals, and then we ask for pins. So a macro is provided to expand the peripherals into pins, which are like pin objects. And then we say, okay, pin.d0, which is one of the pins, make it an output. And then I have an infinite loop where I set high that loop, I delay 500 milliseconds, set low, and then loop again. So because we like live demonstration, I'm gonna run the thing live. So can run. And you will see, yeah, it starts. So that was fast. So it's blinking. So the fun thing is that in the audience last Saturday, there was someone who was the partner of one of my friends, and she was like looking at that, and she saw everybody clapping once the LED was blinking, and we're like, "Are you guys crazy? What is so fantastic about having a light blinking? You're strange people." So that's the first demonstration. So what we saw here is that it has compiled the code, and then it has uploaded the code and written 250 bytes. So my executable is 250 bytes. So when I have 8 kilobytes of RAM, there is plenty of room for quite complex things. And you see that, so I'll give you links if you want to play with that in the end, but the integration of the ATtiny in the Rust environment allows me to just cargo run. I mean, it's all integrated with the cross compilation and everything. So if you look at the command, that was the real cargo run in release mode, and that's it. It's magic. So let's go back to, yeah. So yeah, I would like to show you an expanded version that is without type inference, that is all types expanded. So what we see here is the type is Arduino HAL. So HAL stands for hardware abstraction layer. So that means that a microcontroller basically peripherals are not magic things. They are just like registers that are mapped onto memory. And in order to control those pins, you have to set a bit to 0 or 1 in a register. So it's all driven by memory. The hardware abstraction layer is a wrapper around those registers that gives us more semantic and meaningful methods. And the interesting bit here is that we see the benefits of the Rust type system. So take here will give us an option. So what it is that it's actually a singleton that you can take only once. If we look at the code behind that, so you will have a lot of unsafe code. We see that we have an interrupt-free block, which is important because we don't want to be stopped in the middle of our operation. And then we have a flag that is cleared if we have fetched that peripheral object once. So that means that it will fail if we try to take the peripheral object more than once, which means that you have to take it into your main code, and then wherever else in your code someone tries to access the peripherals, that will be denied. The benefit of that is that then we can use Rust's ownership system. That means that if, for example, here I'll say let d1 equals pins d0, for example, Rust will tell me, hey, you're trying to use a moved value. So that means that by taking pins.0 here, I have extracted a reference ownership of that value into a variable, and then I cannot use it anymore. So by the simple use of the Rust type system and this singleton, we guarantee that no two functions in your system will try to access peripherals at the same time, which avoids mistake like one side of the software using it as an input and the other one as an output, and then having conflicts, hardware conflicts accessing the peripherals. There are also some interesting bits, is that if I do not, let's say, for example, I say, I will duplicate that line and say, I want to make it an input. Yeah, analog input. Oh no, let's into, output high, this one. No, input, sorry. Yeah, pull up input, that one. Why?
It's probably complaining about the type that you have.
Oh yes, you're right. You're absolutely right. So I will just remove that. Yes. So it's still happy, but you see that set high and set low have disappeared because now the type here is no more output here; it's input, right? And those methods are not available on the output. So if we look at that method, how it works. Move that into output, you see that it consumes this parameter and returns another pin in mode output. And in between, what happens is that we set the bits on the microcontroller register that configure effectively the pin as an output, and then we return the same pins, sorry, but with this phantom data here that holds the mode input or output. So if you don't know phantom data, this is something that allows to have a zero type information baked into a structure. So sometimes when you want to have marker types on a type, but there is no associated data structure, you will add a phantom data in your structure, and here this is what holds this output thing. So this technique is called type state programming. That is at the compilation time, our type moves from one state to the other. the initial state of our pins is input floating. Floating means that it has no reference voltage. And then we have to convert it into an output in order to be able to set high and set low. So here we see another benefit of Rust is that because we have this strong typing system, there is no way we can make a mistake. I mean, we have to configure our pin as output before being able to call set high or set low. Otherwise, the compiler will not even allow us to do that. If you have questions, I mean, feel free to interrupt me. So a quick recap of what we just saw.
Well, you may be about to go. There was a question in the chat about what no main means at the the file there, and I think you also have no standard.
Yes. So so no main and no standard. So no main is that, I haven't mentioned that. If you look at the main function here, it returns an exclamation mark. That means that it does not return. It returns it's not that it returns nothing, it's that it does not return, right? This is the syntax in Rust to say this never ends. And this is because we have this infinite loop here. So it's not, in that sense, it's not a traditional main function that is supposed to return at some point. And we instruct the Rust compiler that this is the case by adding this attribute here, saying our module has no main function. And this thing here actually is specific to the Arduino environment and decorates the main function with a specific name and the very tiny thing that is required for the boot process of the microcontroller to actually start the function. The no main here, the no STD. We'll dive a bit more into that later. That means we do not have a standard library. We don't have any file system. We don't have any network stack. We don't even have a memory allocator. So that means that get rid of all of that and only use bare minimal Rust. We'll get back to that in a minute. So the interesting bit is that, and you will find that on every integration hardware abstraction layer for every microcontroller in the embedded Rust ecosystem, peripherals are a singleton object, and you have to consider them as data. So you use the ownership system, and you use typeset programming to transition a peripheral from one state to the other, and then that exposes additional methods. And we also have control mutability coming into play because I cannot, I have to abide by Rust's object sharing rules. I cannot send a mutable pin to one function and to another function at the same time. The compiler would just complain, which avoids, concurrent access to peripherals. In terms of abstractions, so I mentioned, so at the very low level on the right here, we have the microcontroller with its processor and the different peripherals. And for every microcontroller, we have a crate that just is a very thin layer on top of these registers. That is, instead of having direct memory numbers in your code, you have, let's say, GPIO-B, which is resolved into the actual address. And then you have the peripheral access crate on top of that gives you higher level things such as a SIOL bus, an analog to digital converter, so additional layers of abstraction. And on top of that, it is assembled to compose what's called the microcontroller hardware abstraction layer crate. You have the registers on one side, you have the peripherals on the other side, and with that you have everything to start working. And on top of that, again, we will see that later, there is a whole ecosystem of device drivers. We will see later a small display. That display talks I2C, and it doesn't care about the implementation of I2C. So the hardware layer gives us this abstraction. Yeah, I told you it's tiny. I told you 250 bytes that were sent on the wire through USB, but the actual size of the executable is even smaller. It's 174 bytes. So this is the text section of the ELF file. And we see here the BSS section, which is the static data. So what is this 1 byte? This is the peripherals object. That is, I told you there is this singleton file with a flag saying if I have taken the peripherals or not. So this is that 1 byte. So it's really super tiny. And to compare things, I wrote the same thing using Arduino C, and it's 260 bytes big, because the compiler, because of the type systems, heavily, and I would say even aggressively inlines everything. And in the end, if you look at the assembly code, we don't even have a function call. It's all inlined, and it's all flipping bits on the registers. Whereas in C, you still have a few layers of function calls that add a bit of overhead. So in that specific case, it's even smaller than C. Yeah.
Did you try building the C variant with LTO enabled by any chance?
No, that was just the standard configuration of. But you're right. Maybe that would have changed things a little bit.
Okay, cool.
You said LTO, Joel?
Yes, that would like in C you have the translation unit, and I suspect that the bootloader is in a static library of some sort. And if you don't have LTO enabled, then you won't be able to inline stuff from a static library. So if that could explain why it is larger.
Yeah, you're probably right. I should so I should not bitch on C and try again. So yeah, coming back to this no STD thing. So creating an executable also goes through different steps. Rust C is based on LLVM, so it generates the intermediate representation, and then we use LLVM to translate that to whatever target architecture we use. And the thing is that we link with a number of base libraries. So the Rust standard library is organized in roughly 3 different layers. So at the very core, yeah, we have what's called the core layer. So those are the primitive types, and a small number of basic types such as option, result, that kind of thing. No collections, because collections require memory allocation, but you have all the the things that we're used to use when we do Rust all day long. That is all those small tiny wrappers that give typing, and on top of that, you can add, when you have enough memory, an allocator, and then suddenly all the collections become available. But in embedded system, you have to use the memory allocator very carefully, because if it goes out of hand, then your system will crash. And on top of that, you have STD that gives, well, basically all the libc or POSIX layers with the input-output threads and everything. So when we say no STD, it's also no alloc. That is, we just have the core types. And in some environment, you can add an allocator when you have enough memory, and in that case, you can use the collections. So another demo, and yeah, because we only had output, so let's see with an input. So IntelliJ is here. So if I show you, yeah, so you can see here maybe this thing here is this one here is a photo resistor, and we're going to change the blinking rate according to the light. So we create an analog to digital converter. So the interesting thing is that internally, those are things that run in iteration until they find the proper value. So you have to indicate them what is the clock frequency of your microcontroller. And we see here that our pin is not an output anymore, it's an analog input, and we pass the ADC. So the ADC is able to, it has, I think, 4 channels, and you can add multiple pins to the ADC. And then we can use analog read and hey, it has to be a mutable reference. The type system here still comes into play. So if we blink with sensor chip, and then if I put my finger here, you will see it slowing down, and with the light, become stressed. Yeah, too much light.
So cool.
Yeah, so you see here that I limit the sensor value to maximum value because I made the mistake of not limiting it, and I went above the number. I had an integer underflow error, and then suddenly started to wait for 1 minute. All right, so yeah, so this is the code that we just saw, and now we are going to use this guy here. Oh, window doesn't want to. How interesting. So the camera window doesn't want to go over from. There you go. So this guy here. So what we see here is that. So the microcontroller itself is that metal thing. It has a metal shield because there is all the Wi-Fi and Bluetooth radio frequency systems underneath. We have the Wi-Fi antenna here. It's a small PCB, and everything else is like the USB chip, voltage regulator, and a few things. And also, yeah, this one is a nice RGB LED if you want to blink on the board itself. And then we have on the other side a tiny screen, which is 128 by 64 pixels, so super tiny, but useful if you want to display things on your experiments. So going back here, yeah, so this one is big, so 16 megabytes of flash, so that means that you have plenty of room. Yeah, 0.5 megabyte of RAM, and also 8 megabytes of pseudo-static RAM, which means that it's a RAM that has lower access speed, but like you have in vast amounts. So when you have something that has 8 megabytes of RAM that is so small, you can do a lot of things. If you have a Wi-Fi enabled device in your home, be it a light bulb or a smart anything, and it has Wi-Fi, there is a high chance that it has a chip of that family in it. And most of them are hackable and actually hacked. You will find alternate firmwares on GitHub. The way I use that in my home. So here you see that this is the kitchen garden watering system that is controlled by a microcontroller. So it's then controlled by the weather station. I also have it running for a custom weather station that displays rain and temperature information. So it's actually hidden behind that screen. It's an e-paper screen. So you can do very interesting things with those devices. Yeah, so once you start playing with that, I have that on my wall. Actually, it's a description of all the pins. They all have multiple functions, so you better have this handy. So with so much space and so many peripherals, how do we actually use that? So it comes with an embedded real-time system. It's hard to use that with pure bare metal, because if you want to use Wi-Fi has some background tasks. It needs to periodically talk to the access point and that kind of thing. So there is no real way, or it's going to be very hard to use Wi-Fi on a microcontroller if you don't have some kind of task scheduler. So it uses free RTOS, free real-time operating system, which is an open source thing written in C that provides multitasking, memory allocation. Yeah, alloc timers, message queues, and that kind of thing. And then the maker of that microcontroller, Espressif, also is very much involved in providing software libraries. So we have everything out of the box to use Wi-Fi and Bluetooth with also they do provide ways to do sensor networks without an access point. So you can have mesh networks of microcontrollers. And then even higher level things such as out-of-the-box MQTT client, TLS encryption, and an HTTP server and client. So having an HTTP server on that kind of thing is pretty nice. Multicast DNS for, like ZeroConf, Avahi on Linux for service discovery. SNTP, so you have network time protocol integration, and then something that is more industrial, Modbus, industrial bus, and CAN, which is the bus you have in your car. So you can plug that on your car diagnostics plug and then start monitoring what's going on inside. They provide also out-of-the-box FAT file system and SPIFFS, I don't know how to pronounce that, which is a file system dedicated to flash memory that allows the tiering effects of usage of flash memory, and even POSIX threads and IPC and logging facilities. So it's not exactly STD, but it's becoming pretty close, and it's very interesting. So there are two main crates libraries in that ecosystem. So the sys crate is basically just a Rust binding on top of all their C libraries, and then a group of people they have now hired are working on a higher level abstraction, which is purely Rust and purely safe, whereas the sys crate is only C bindings that are completely unsafe. So that means that using this ESP IDF SVC crate, service crate, we can program the thing with the comfort of the controls given by the Rust compiler. So yeah, hello world on the tiny display. So I'm going to show you the code. Window. There you go. So here we can print, wow, because we have a serial line, and the USB establishes a serial line, and we can see that in the terminal. Just as previously, we will take the peripherals, and here we will instantiate an I2C bus, which is a serial bus, because our tiny display talks I2C, and we say, okay, initialize it using well, this is the internal driver for the I2C, and we configure it with 2 pins, which will be plugged from the microcontroller to the display, GPIO2 and GPIO3, and some configuration defaults. They just work fine. And on top of that, we will move up into the abstraction layer. So we have the display is its model name is SSD 1306. That's the name. And we have a crate for that. It's basically a driver. That is, it knows the protocol that implements the screen, and we instantiate it by saying, okay, I connect you to this I2C master service that I just instantiated. And on top of that, again, we will create an actual display. That one was just a simple driver, and the display is something that gives me graphic primitive to draw lines, circle, text, rotation, colors for multicolor displays, and so on. And then we can display, and here below, I will run it now because it takes a bit longer. Yeah. And then you see we create a text object and we put it on the display, and that's it. So we have like fonts, sizes, alignments, and everything. So we can do fancy graphics if we want. Okay, so I found that.
Question here.
Yep.
The font size is pixel by pixel per pixel.
Yes.
Ah, cool.
Yes. Yes, you don't have like a points abstraction or that kind of thing because we don't know what is the actual DPI of the display. It's just pixels. So here it is uploading. So it's a bit longer because of course it's bigger. So the executable size for that demo is, I think it's something like 260 kilobytes. So it's 1,000 times bigger than on the previous one.
But that probably does include the RTOS, right?
Sorry?
Does that include the RTOS, the free RTOS, or is that not?
Yes, everything. Yeah. So we have
Okay.
the free RTOS, we have the Wi-Fi libraries, we have everything. So yeah. So my screen is a little bit dark. We can switch that light off.
It's visible.
Yeah. There you go. Hello world. So you see that the red and orange wires here are on GPIO 1 and 2, and they go to the pins of my screen. So it's, yeah, I mean, it takes a while to understand the logic of those different layers, but once you get it, and there are plenty of examples, it's pretty straightforward. And again, the Rust compiler will help you here. So yeah, here's our display, about €2 if you buy it on Amazon. And yeah, so what I just explained, that is the different layers of abstraction. So at the high level, we have our application that talks to embedded graphics, that is just deals with a text object and display. And that thing is implemented on top of the SSD screen implementation that goes down to the I2C bus implementation and finally goes to the microcontroller registers. So depending on what you're working on, you will use those different layers. But of course, we will try to stay at a high level, which is more comfortable and also more portable. And last demonstration, an embedded HTTP server. I like that one because it doesn't seem obvious that you can run an HTTP server on that kind of thing. So that will be where is it? Yeah. So that one is a bit more involved in terms of code because of course we have to set up everything. So I will still keep my screen. Yeah, so here I'm also adding just as we had previously the light dependent resistor, and we will display we will publish that information on a web page. So that means that I have to, yeah, I will first start. So let's have a look at Wi-Fi initialization. So we have to create a network interface. So this is the TCP stack that we have to instantiate. So we just take the default configuration. This one is the internal event loop. You have to create this event loop that is a shared resources that can be used by the different tasks. That one is non-volatile storage. I don't know what it's used for, but the Wi-Fi stack is that. And then we're going to configure it. So where it gets interesting is that you say, okay, I'm creating a Wi-Fi object and I will scan. So what it does, it scans the different Wi-Fi channels and searches for the different access points. And then we have our SSID. So I have here this little structure where I have configured the SSID and password. And we just get all the list of access points and filter it looking for our own access point. If we find it, then we will connect. And where it gets interesting is that if there is a mixed mode in the Wi-Fi stack, where if it doesn't find the access point you're looking for, it will create its own access point. Then you can connect, enter the credentials of your access point, and then restart the Wi-Fi stack to actually connect to your Wi-Fi. So this is something that is pretty common when you have a Wi-Fi enabled smart device. That is, you first connect to the device, enter the credentials, and then it actually connects to your home. So this is how it's done. That is, you start your Wi-Fi in mixed mode, and it will switch from a regular access point or its own exposed access point, depending on whether it finds the one you're looking for or not. So we get our access point. I won't go over the details, but I will just output the IP address. And once we have that, we can create our HTTP server. Where is it? Yeah. And that's magic, well, in my opinion. We create an HTTP server with the default configuration, which means that HTTP on port 80, HTTPS on port 443. It's not enabled here because we haven't set TLS certificates, but you can also put your own certificates, of course. And then we have something that is very common when we work on servers. There is, we describe our routes. So those are just pass prefixes here, and then we have a closure with request and response, and we can set status, send headers, and send content. So it's just a regular web server. So I'm gonna start that. Oops. Where is it? Yeah, wrong window, of course. So it's so the HTTP server will just give us a home page, and then there is a light endpoint that will output the current light sensor and refresh. Nothing fancy here, but the purpose is to demonstrate the HTTP server. Okay, that one is a little bit bigger. Any questions so far?
Yeah, it means that you could control via the HTTP server even the pins attached to the board, right?
Absolutely, absolutely.
Awesome stuff.
Yeah, I mean the number of possibilities it opens is just endless. Once you have an HTTP server that is connected to the physical world, it's so I showed you previously briefly my garden watering system. It's just that is you have an HTTP server that exposes switches, which are actually relays that open the valves. So where is it should have output. Yeah, access point. Oh yeah, because my configuration is not the right one. It's not the example one. So I'm sorry, I'll have to wait a little bit more. I don't know if you know this include macro here. It is obviously on a microcontroller, we don't have environment variables because there is no environment. So the credentials here, I did hard code them using this kind of file. So this is just like the structure initialization, and I import it in the code using the include macro.
You can make it a const. It's cool.
Yes. Yes. Yeah.
Or you have to make it a const to use include.
In that case, I have to make it because I mean I could have included that in the function, but here it's declared outside of the function, so it has to be a const. But I think maybe I could have maybe saved a little bit memory. No, because the memory would have to be allocated for the strings anyway, so that wouldn't change anything.
So you're doing all this on Mac. Any issue with the development tooling for the ESP32? I guess it's pretty easy with Cargo, I assume.
Yeah, I mean, it's very well integrated, and you know, since we install a cross compilation toolchain here, the people from Espressif even provide an ESP up thing that is very similar to Rust up, which is just dedicated to installing the toolchain. So you just ESP up and the name of your microcontroller, and you're done. It works.
That's awesome.
Yeah, it works on Mac. It works very well on Linux as well. I haven't tried on Windows, but I mean, it's very cool. So we maybe after that can go further in this configuration here, because this is where all the magic lies. But once that is configured, and it's mostly a copy paste, you don't have to think about it anymore. So here we go. So okay, so this is my little microcontroller talking. So yeah, so you see on the screen I am displaying the current light sensor. So I will go to that page there, and we will see that it changes. Yeah, magic. Love that. This is so cool. Close it a little bit. Yeah. So there you go. Just wanted to show you how, yeah, there is some things that you have to take care about. Where is it? Yeah. Where is it? Yeah. So you see here, light value is an atomic number, and it's an arc that is with an access counter. So it's a shared variable that will be used by different tasks. One task will be the one that updates it periodically, and the other task is the web server that publishes it. So we have to abide by Rust's rules regarding concurrent access to data. And here I am wrapping this value into an arc, because it's shared between different tasks. And then the loop, where is it? Yeah, the loop here gets the value from the analog to digital converter and stores it into the atomic integer. And then on the other side, the HTTP server will read that value. So where is it? Yeah, light.load here. So I would say nothing fancy here. You just have to use Rust's concurrency primitives. But by just saying that, I mean, this also saves a ton of possible mistakes. If you're using C, usually you will just share a memory address with all the race conditions that come with that. So we just use Rust's memory concurrency primitives, and everything comes for free. And I think, yeah, we're pretty much at the end. Yeah, so conclusion. So really runs everywhere. I like this super tiny demo. It's very also suited for embedded development. And the interesting bit is that it's not only hobbyists, very serious companies are using it right now. There are some ongoing efforts to have a Rust toolchain that is certified for mission critical systems. So we're talking serious business here. Yeah, the other thing is that modern microcontrollers are basically as powerful as the PC I had on my desk like 20 years ago. And there is a lot more to say. We haven't touched about async await. You can use async await, which gives you like concurrent tasks with a very tiny footprint. Interrupts, how to interact, with buttons, that kind of thing. Debugging on the wire. How do we debug on that thing? It's also possible. It's well integrated. We can do also over-the-air updates. That is, once I have uploaded my firmware once, I don't have to plug it into a USB cable anymore. I just update it wirelessly, and so on and so on. So there is still a lot to say. And that's it. So I will put the link to this in the Google Doc for the Rust Guild, and you have everything there.